I apologize. My mouth seems to be acting a little strange, but I'll try to hopefully try to get this right here. Hopefully everybody can see this here. So it's my pleasure today to welcome Ed Barnes for Virginia Tech for our ARC seminar talk. Ed is he's a professor in the physics department at Virginia Tech, where he has been since 2015. Prior to that, Ed held a postdoctoral position at the University of Virginia and a senior research associate position in both the Joint Quantum Institute and the Condensed Matter Theory Center at the University of Maryland. Ed earned his doctoral degree in physics in sunny California from the University of California, San Diego in 2006. Today, Ed is joining us to speak about some of his recent work and towards efficient quantum simulation on near-term devices. So with that, Ed, please take it away.
Hello, Greg. Yeah, and thanks a lot for the opportunity to tell you a bit about what we've been up to at Virginia Tech. So I'm going to focus on quantum simulation on near-term devices for today's talk. So as we're probably all very well aware, it becomes really challenging to simulate quantum systems on classical machines. And so we quickly run out of space to solve even modestly sized problems, making it challenging to answer some basic questions about many-body systems, as well as many other types of problems that people are interested in. And of course, the basic idea usually attributed to Feynman is that we can replace the classical machine with a quantum machine and try to simulate other quantum systems using this controllable quantum device. And there are two different ways in general that people go about trying to do this. So one is called analog quantum simulation, where the idea is that you take a quantum system and you try to create the Hamiltonian of the system of interest on this machine. And then if you can tune the parameters, you can study that problem Hamiltonian in various regimes and try to understand something more about the physics of a problem. There's another approach called digital quantum simulation, where instead of trying to recreate the Hamiltonian on the quantum device, we're going to use the quantum device as a digital type of machine where we can, in principle, solve any type of simulation problem of interest. And in this talk, I'm going to focus on the case of digital quantum simulation exclusively. So the first question in this type of simulation task is, how do you map the problem of interest onto this quantum device consisting of some number of qubits? And we can illustrate this with the case of fermionic Hamiltonians, for example. So this is a standard second quantized Hamiltonian describing a collection of electrons with single particle terms in the first part here, and then Coulomb interactions between pairs of electrons represented by the second term. And now there are many different ways we can map this kind of Hamiltonian onto a quantum device. The most commonly used one is Jordan-Wigner, where the qubit 0 state corresponds to an orbital being unoccupied, and the 1 state corresponds to the orbital being occupied. So for every orbital we have in the original problem that we're trying to simulate, we have a qubit. And an important feature of this, of course, is we need to not only map states, we also have to be able to map operators. And the basic operators on the fermionic side are creation and annihilation operators. But because qubits are distinguishable, unlike fermions, we have to include additional Z strings in this representation of the creation operator, for example, in terms of qubit operators, to account for that those fermion statistics. So one of the most promising approaches to realizing quantum simulation on near-term devices is to use variational quantum eigensolver algorithms. So the idea is that we use both a quantum processor and a classical processor in tandem to solve problems. And the idea is that we try to offload as much of the work as we can onto the classical machine and use the quantum machine primarily to store the many-body wave function, which is the main thing that's challenging for a classical computer. And so the idea is that we first take our problem system, for example, a molecule, and then we map this onto the quantum computer using, for example, the Jordan-Wigner approach I mentioned on the previous slide. And then we want to somehow update the wave function of this quantum device by doing measurements and taking into account the results of those measurements. We can figure out how to update the parameters describing the circuit that prepares the state on this device. And the basic principle that we're using here is the variational principle from undergraduate physics, where we're trying to minimize the subjective function, which is just the expectation value of the Hamiltonian, with respect to these parameters in the state preparation circuit. So that's the cost function, but of course there are many different ways in which we can construct the state preparation circuits that depend on these parameters theta. So some of the two most commonly used choices are called hardware efficient ansätze, where the basic idea is that we use native gates on the hardware. But this has some drawbacks. One is that it tends to be inefficient in the sense that it tends to sample too much of the Hilbert space, beyond the regions where we know the solution has to be found. And also it's been shown more recently that these types of ansatz are difficult to optimize, and they can lead to issues, for example, called barren plateaus, where the optimization procedure gets stuck in some irrelevant part of the parameter landscape. Another commonly used choice for ansatz is chemistry-inspired and usually called unitary coupled cluster. A nice feature of this approach is that it respects the symmetry of the problem. They're built into the ansatz. But some challenges are that the state preparation times tend to exceed coherence times. This ansatz is not guaranteed to be exact in the sense that it's not guaranteed you can exactly represent the target state you're after. And it's also ill-defined if you do a low order trautorization, as we showed in a recent paper. So an issue with both of these approaches is that they use very little information about the problem that we're trying to solve. And so kind of the main theme of this talk will be the more information we use about the problem we're trying to simulate, the better the ansatz will behave. So here are some experiments using these ansatz that the people have tried. So for example, the hardware efficient ansatz was first demonstrated by the IBM group back in 2017, where they constructed a layered circuit consisting of single qubit gates that are parametrized, interspersed by basically free evolution under the coupling of the different qubits that creates entanglement. And by doing a sequence of these kinds of layers, they were able to create different states, trial states for the optimization process. And they tried this approach on several different molecules like H2 or lithium hydride or beryllium hydride. In all cases, they found reasonable, at least qualitative agreements, in some cases quantitative, but there's still noticeable differences even for these modestly sized molecules. And I think this is largely due to the issues with hardware efficient ansatz, running up against coherence times and things like that. Here are some examples in which UCSD ansatz have been used. So these have been used in all kinds of different physical platforms, including photonic qubits, trapped ions, superconducting qubits, and spin qubits, all with decent success. But again, even for these really modest problems, H2 is a very simple problem. You don't get perfect agreement. And this is, again, because of these limitations of these ansatz. By the way, I forgot to mention that if there are any questions during the talk, please feel free to interrupt me. So what are the properties of a good ansatz? So a good ansatz should span the subspace where the solution lives. For example, it should span the right symmetry subspace if we know something about the symmetries of the target state we're after. The resulting state preparation circuit should be shallow enough that we don't run up against coherence time limitations. It shall not have too many optimization parameters because classical optimizers, although in VQEs we're trying to offload as much of the task onto the classical machine as possible, classical optimizers are not infinitely robust, and so we need to also make sure we don't overwhelm them. And similarly, we also want to make sure that the landscape of the cost function is not too complicated so that the optimizer does not get stuck. So trying to achieve all of these at the same time in the same ansatz is notoriously difficult, but I'm going to hopefully try to convince you that some approaches are better than others in this respect. So regarding the outline of the talk, I'm going to show 3 different ways to try to address these issues. And these are sort of in order of how flexible the ansatz is and how informed it is about the problem being solved. So the first one is symmetry enforcing state preparation circuits, where we construct state preparation circuits that exactly know the symmetries of the target state that you're trying to find. And then at the next layer of problem tailoredness, as we'll see, is a class of adaptive algorithms that we call ADAPT-VQE. And I'll spend most of the talk discussing this class of algorithms. I'll talk about how to build symmetries into them, how to use them for optimization problems, and how to use them for preparing not only pure states, but also Gibbs states. And then in the final part of the talk, I'll say a bit about our more recent work on trying to go beyond gate-based approaches to variational quantum eigensolvers, and instead using pulse-based approaches. And this we call ctrl-VQE. But the general theme is that we want to make the ansatz as problem-tailored as possible. It should know as much about the problem that we're trying to solve as possible. And the features that we're after, again, are shallow circuits, minimal number of optimization parameters, and exactness. And so first, let me say a bit about symmetry enforcing circuits. So we can make a circuit that respects the various symmetries that we expect to see in the target state. So for example, if we're solving an electronic structure problem, like a molecule, then we typically expect that particle number is conserved and spin symmetries as well. So if we just focus for a moment on particle number symmetry, we can note that if we have n orbitals, then this means we have n qubits under Jordan-Wigner. And then an arbitrary state can be described by 2 times 2 to the n minus 2 real parameters, accounting for normalization. So if we have a system of n fermions, the minimal number of variational parameters is combinatoric in these two numbers. And then what we can do is just build up a state preparation circuit using components that respect this particle number symmetry. And a basic ingredient that we use are these so-called A gates that were first introduced by the IBM Zurich team back in 2018. So this is a 2-qubit gate that only mixes the 0, 1, and 1, 0 states so that the particle number is conserved when you apply this to any state. And it has 2 free parameters, theta and phi. And if we're only interested in cases where time reversal symmetry is respected, which is typically the case for a molecule, at least not subject to a magnetic field, then we just have 1 free parameter, this theta angle. And what we showed in this work from 2020 is that if we basically construct a state preparation circuit using this bricklayer type fashion, after we first bring the initial all 0 state into the right particle number subspace using X gates, then we can generate any particle number preserving state using the minimal number of parameters, which is this 2 times n choose m minus 2. So what's nice about this is you expand the target symmetry subspace exactly once by tuning these parameters. So it minimizes the number of parameters you need to do that. And we only use nearest neighbor gates in this construction, making it friendly for hardware in which that's typically the case. So here are some results showing how this works. So this is a plot of the number of C-naughts in the resulting state preparation circuit versus the number of fermions, m. And compared to other approaches to constructing particle number preserving state preparation circuits, we seem to always do at least as well, and in most cases, orders of magnitude better. Primarily because our circuit is designed to minimize the number of optimization parameters, unlike previous approaches. And then we've tested it in various simple problem examples, like the H2 ground state, for example. This is results from running it on IBM hardware. And compared to built-in ansatz on the IBM devices, we find that we reduce both the number of parameters in the ansatz and the number of C-naughts pretty systematically. And details about these hardware simulations can be found in this work here. So in addition to particle number, we're also typically interested in spin symmetries like total spin or the Z projection. To enforce the Z projection preservation, that's very simple to do based on the particle number conserving circuit that we've already designed. All we need to do is just order our spin orbitals so that all the spin up orbitals are in the first n over 2 qubits, and all the spin down ones are in the second n over 2 qubits. And simply by ordering our qubits in this way, we automatically get a circuit that respects the Z projection, with the one minor additional point being that for every A gate that connects these 2 different spin registers, we have to set the parameters to 0. But this does not mean that we don't create entanglement between the 2 registers, because if you notice what the A gate looks like here, if theta is set to 0, this is actually a CZ gate. So it's a maximally entangling gate when that parameter is 0. Now, if we also want to enforce total spin conservation, then we have a different approach for doing this. Essentially, what we do is we parameterize all the states that span the total spin subspace using hyperspherical coordinates. And then we found a set of constraints on these angular variables appearing in this expression that guarantees that you exactly span this total spin subspace once. And then given this parameterization of an arbitrary state in that subspace, you can back out a gate that we call an E gate that implements that takes you from the initial state to any one of these states. Okay, so that's all I'm going to say about symmetry preserving circuits. Next, I want to kind of move towards a higher degree of problem tailoring, and this brings us into these adaptive algorithms known as ADAPT-VQE. So ADAPT stands for Adaptive Problem Tailored Variational Quantum Eigensolver. This is the first dynamically created ansatz that we're aware of. Basically, the problem Hamiltonian dictates how this ansatz is constructed. So we start from a simple short depth ansatz, for example, a Hartree-Fock state, if we're talking about a chemistry type problem. And then by taking measurements on the quantum processor, we determine how we should add additional operators on, acting on this initial Hartree-Fock state to build up the ansatz, one operator at a time. And since these measurements depend on the Hamiltonian and they depend on the state of the processor at that given point in the ansatz construction, this is an intrinsically problem-tailored ansatz. So here's a quick overview of how the algorithm works. So sort of a key ingredient in the algorithm is the operator pool, the operators from which you decide how to build up the ansatz. And then given such a pool, I'll say a bit more how we should choose these pools. You initialize your quantum processor in an appropriate initial state, for example, Hartree-Fock. And then we measure the gradient with respect to each of these operators. So the idea being that we sort of test out each of these operators one by one, and then see which one changes the gradient the most. And you can show that the derivative of the energy with respect to this new parameter that comes along with inserting this operator into the ansatz is essentially given by the expectation value of the commutator of the Hamiltonian with that operator. And so we do this for each of the operators in the pool, and then we select the operator that gives the largest gradient. We add that to our current ansatz, and then we re-optimize all of the parameters that have been inserted into the ansatz so far. And then we continue, and then we again consider adding an additional operator at the next layer, choosing the one that gives the largest gradient, and so on. We keep iterating until all of these gradients are below some target threshold, in which case we then say that we have converged and we can extract our answer. So here are some results for ADAPT-VQE in the case where the pool is comprised of fermionic singles and doubles operators. So here we're looking at the energy as a function of bond distance for 3 different molecules, lithium hydride, beryllium hydride, and H6. And on this scale, so here I'm plotting the Hartree-Fock result, which is the green curve, which never works very well, so we shouldn't pay too much attention to that one. But then we also have here the exact result obtained from full configuration interaction calculations in blue. And then UCCSD is in orange, and then 3 different versions of ADAPT are dashed lines, red, purple, and brown. Okay, but on this scale, we can't really see the differences between most of these curves. So if we zoom in and look at only the energy difference on a log scale, we can start to see the differences. And we see that by going to higher and higher precision adapt, where here the precision is just set by deciding what the threshold on the gradient should be, we can always outperform UCCSD. And this is true for each of the molecules that we've studied.
Sure.
And in addition to that, we can ask how many parameters do we need to attain that improvement. And in each case, we see that we can use fewer parameters and get better accuracy. So for example, in the case of lithium hydride here, all 3 versions of ADAPT have far fewer parameters compared to UCCSD, which is just a fixed ansatz. It's not tailored to the problem at hand, aside from symmetries. And so it always has the same number of parameters regardless of what the bond distance is, whereas ADAPT adjusts itself depending on what the bond distance is. Now there's one exception here where ADAPT requires more parameters to get better accuracy, but then if you compare what's happening in terms of energy accuracy, we see that it's using more parameters exactly when it needs to. So here, UCCSD is failing to achieve chemical accuracy in this H6 example for bond distances above about 1.2 or 3, but ADAPT is able to still get well below chemical accuracy, but at the expense of needing more parameters. So this adaptive algorithm is deciding when does it need more parameters and when does it not. And in that sense, it can be very efficient. Now, what happens if we take the operators that were selected by ADAPT and just scramble their order? How important is this? Is the order that ADAPT finds? And that order is determined again by using this gradient condition. And what we see here, so here in orange and blue are two different versions of ADAPT, two different pools, one using singles and doubles and one using generalized singles and doubles. Again, fermionic operators. We can compare this to different random orderings and lexicographical orderings of the operators. And we see that the order in which the operators is chosen in ADAPT is very important for the convergence properties. And by the way, UCCSD is somewhere up here. So I also want to briefly comment on the trainability of ADAPT. So ADAPT dynamically creates these ansätze based on measurements of the quantum processor. How difficult is the optimization process? So in every iteration of ADAPT, we have this VQE subroutine where we re-optimize all the parameters sitting in front of all the operators that we've added to the ansatz so far. How challenging is that subroutine? So, it's nice that ADAPT produces compact problem-tailored ansätze. So the circuits tend to be shallower, but is the landscape very rugged? Can we get stuck in local minima? And do we have barren plateaus issues? So how trainable is this algorithm? And so to try to answer this question, what we did was we tried to relax the assumption that every time in each iteration of ADAPT, what we normally do is we set all of the parameters for the VQE subroutine to the previously optimal values. But now if we relax that assumption and instead just take random initial guesses for those parameters for each VQE subroutine, then we can sort of explore what the landscape looks like of the cost function. And so that's what this plot is showing. So here each little dashed line corresponds to a different random initialization. So here I'm looking at the energy error logarithmically along the y-axis versus the number of parameters in the ansatz. And so this is basically a plot of the landscape of the cost function for this problem. This is H6 at a bond distance of 3 angstroms. And so what we see here is that if we always use the previously optimal parameters in each iteration of ADAPT that corresponds to the green curve here, that always gets very close to minimizing the energy as much as possible. Whereas if I use a random initial parameterization, random initial parameters for that VQE subroutine every time, then I can get stuck in local minima. And we can see from this plot that there are many, many, many local minima. So this is a very rugged landscape. But if we use the standard ADAPT of always using the previous optimal parameter values, then we never really see any of these local minima, and there's no issue with trainability. In a similar way, ADAPT also avoids issues with barren plateaus. So barren plateaus are very flat regions in the parameter landscape where the optimizer can get stuck because it's unable to distinguish a preferred direction, if it's a gradient-based optimizer at least. But what ADAPT essentially does is early on in the algorithm, it will pick a local minimum. But then since it's building up the algorithm, it's building up the ansatz, operator by operator, it's basically choosing its own parameter landscape. And the way it does that is it basically converts what's initially a local minimum into a global minimum. It takes that initial local minimum and it keeps making it deeper and deeper. And so the algorithm works in such a way that it's always close to this global optimum in the parameter landscape, which is why it doesn't really care about local minima, why it doesn't really care about barren plateaus. It always stays in the relevant part of parameter space. And one way we can understand why this happens is because since we build up the ansatz operator by operator, every time we run the VQE subroutine, all the parameters except for one are set to 0 essentially because we're already at the optimum in that case. And so there's only one direction in parameter space that has a non-trivial gradient, and that gradient by construction is large. And so again, this is why things like barren plateaus are not really an issue. Okay, so I've only talked about fermionic operators in the ADAPT pool so far. So I wanted to say what happens if we consider other choices. And a natural choice is to use Pauli strings, for example. So one challenge with using fermionic operators is that they tend to be long linear combinations of Pauli strings. And so when you translate them into gates, you can end up with long sequences of gates. Although there have been some recent results showing how to reduce the gate that corresponds to fermionic operators. Can we instead just use Pauli strings as our pool operators, and in this way make a more hardware efficient type pool? And the answer is yes. So a natural choice to try is to use Pauli strings with up to 4 Paulis. And this idea was considered in this PRX quantum from last year. And here are what the results look like for this other type of pool. So here I'm looking at the energy error as a function of adapt iteration number in the first row here for molecule H4, lithium hydride, and H6. And here the blue curve corresponds to the Qubit adapt using these Pauli strings in the pool instead of fermionic operators, whereas the red curve corresponds to the original adapt based on fermionic operators. And you can see that the convergence for the fermionic case is much faster compared to the Qubit case. In some cases up to a factor of 5 or so as the problem gets larger. But now if we translate those ansätze into state preparation circuits and ask how many C0 gates appear in that circuit, it turns out that for Qubit adapt, the number is much smaller compared to using fermionic operators in the pool. And even if you transpile those circuits built from fermionic operators, the improvement afforded by Qubit adapt is still significantly larger. And basically, this is just because we're using these Pauli string operators, which have a much simpler circuit representation. So more specifically, how should I choose the operators in the pool? So in the results from the previous slide, I considered all possible 4 Pauli strings of weight 4, but can I use a subset of those and still get very good results? And this is an important question because the smaller the pool, the fewer measurements I need to do in the VQE. Right? Because every time I run an iteration of ADAPT, I have to measure the gradients with respect to every operator in the pool. And so the smaller the pool, the fewer number of measurements I need to do in each iteration. And also, can we take into account hardware constraints and things like symmetries and so on to further speed up the conversions and reduce the overhead on quantum hardware? So this led us to the idea of complete pools. So what is the smallest number of operators in the pool we need to guarantee that we can take any initial state to any final state? And this is a relatively straightforward exercise in group theory and Lie algebras in particular. So if I have an adapt type ansatz where I have a sequence of exponentiated pool operators like here acting on a reference state, then the question is, what kinds of terms can I generate by looking at the commutators and the commutators of these pool operators? And if I can generate enough of these different operators, then I can exactly span the Hilbert space by applying this sequence, this product of operators onto my reference state, no matter what the reference state is. And essentially what this means is that if all the operators coming out of these commutators, when applied to this initial reference state, form a complete basis, then I can represent any state in this way. And so in this way, I can guarantee that my ansatz is at least in principle exact. And if you try this for random Hamiltonians for small numbers of qubits, so for 3, 4, or 5 qubits shown here, you can see what the difference is between using a complete pool versus an incomplete pool. And if the pool is not complete, then you're not guaranteed that you can get to the target state you're after. And so oftentimes in those cases, we find that the algorithm doesn't converge. But if you always input a complete pool, then ADAPT seems to converge successfully. So this is at least so far as there are no symmetries in the problem, which is the case for these random Hamiltonians. I'll come back to the issue of symmetries in a second. Now, so completeness is an important criterion for ensuring that the ansatz can be exact, can exactly represent the state we're after. What is the smallest number of operators we need to get a complete pool? And the answer is 2n minus 2, where n is the number of qubits. So it's linear in the number of qubits. And here's an example, an explicit example of a minimal complete pool for an arbitrary number of qubits. And in this example, you can see here that each of the pool operators is a Pauli string of weight 2, and it only acts on nearest neighbors, at most nearest neighbor qubits. So it's a very hardware-friendly pool in that sense. So that's an explicit example of such a minimal complete pool. And in the work shown here at the bottom of the slide, we have proven several things about these minimal complete pools. First of all, that this particular pool is complete. We've proved that 2n minus 2 is the minimal size of a complete pool. We found 3 different criteria for identifying when a given pool is minimal and complete. And we've shown how to incorporate symmetries into these minimal complete pools. So I'm not going to go through all the details of the different proofs. I will flash briefly for a moment what these three different criteria are for how you can tell if a given pool is minimal and complete. So the following three statements are equivalent. So a given set of operators is complete. That's equivalent to saying that the pool cannot be split into two mutually commuting sets. So given a pool, can you divide it into two sets such that every element of the one set commutes with every element of the other? If that's the case, then the pool is not complete. And so that we've proven. The reverse statement we have not quite proven, which is that if you cannot split the pool into two mutually commuting sets, is it guaranteed to be complete? We believe the answer is yes, and we have lots of numerical evidence for that, but we don't yet have an analytical proof of that statement. And this second condition is the most important one because it's the most efficiently computed. It's very easy to take a pool and compute whether or not it can be divided in this way. And so that's the one that we typically use to determine if a given pool is minimal and complete. Okay, what about the role of symmetries? So most problems of interest have, Hamiltonians that respect various kinds of symmetries. How does that impact the performance of ADAPT? We have noticed that there are two basic issues that can arise in the presence of symmetries. One is that ADAPT does not start at all. It's never able to find the first operator to add to the ansatz. Another issue can be that it does start and gets to a certain point, but then it fails to converge. It just gets stuck. And both of these can be attributed to issues related to symmetries, and they can be solved. So, so what happens in the case of symmetries is that the gradient criterion may not allow exiting a symmetry subspace. And so if your pool does not respect the symmetries of the problem Hamiltonian, then you can get stuck. So for example, if you start off with a Hartree-Fock state that has certain symmetries, and you try to apply a pool operator that does not respect those symmetries, then it's not going to be added to the ansatz because it's going to not be selected by the gradient criterion. Or later on in the algorithm, after you've moved away from the Hartree-Fock state, there we can have various types of parity symmetries conserved, including inversion or particle number parity, for example. And again, if we try to add a Pauli string to the pool that does not respect these symmetries, then the gradient criterion is going to give us 0. It's not going to select that pool operator. And so if we don't have enough symmetry preserving pool operators in our pool, then ADAPT is not able to function properly. And so this is an example over here, the lower right plot here, of what happens in the second scenario where the algorithm starts, but then eventually gets stuck because there are not enough symmetry respecting pool operators. So here we see that it starts off and the energy is getting lowered, but after some iteration, like the 11th iteration, it gets stuck at some energy value, which is not sufficiently close to the target energy we're after. So how do we fix this problem? The answer is to use symmetry preserving minimal complete pools. What we need to do is to look at the symmetries of the problem Hamiltonian and build those into the pool operators. And you can do this systematically. In the case of getting the algorithm to start, an additional consideration that has to be taken into account is we need to use two particle excitations in particular because Hartree-Fock is the lowest energy product state. So if we try to use single particle excitations on top of that, they're not going to be selected by the gradient criterion. So we need to have at least some two particle excitations in our pool to guarantee that ADAPT can take us away from Hartree-Fock. But then aside from that, we just have to make sure that all the pool operators respect the different parity symmetries in the problem, the ones related to particle number, inversion, and spin. And you can systematically do that using some fairly straightforward group theory analysis. And what tends to happen is that you need fewer pool operators, even less than 2n minus 2 in the case of symmetries, because now we're just exploring a smaller symmetry subspace of the full Hilbert space. So we no longer need to go from an arbitrary state in Hilbert space to any other state using these pool operators. We only have to go from a state within the symmetry subspace to another state in the same subspace. And so, for example, in the case of this H4 molecule example, so this is the red curve is what I showed you on the previous slide, where ADAPT got stuck because it had the wrong types of pool operators, the ones that did not respect the symmetries of H4. But if you correct for that and change what the pool is, then even using a smaller pool with only 11 operators in this case, you can reach convergence. And if you're curious, this is what the precise pool looks like in this case. So it has 11 different non-trivial 8-qubit Pauli strings. Okay, I also wanted to briefly mention a couple of other directions in which we've taken this ADAPT idea. So one is in the preparation of variational Gibbs states. So instead of preparing pure energy eigenstates, we can try to use variational methods to prepare systems at finite temperature in a Gibbs ensemble. And since the state is no longer pure, this means that we generally need to have ancilla qubits in order to create mixed states. And a challenge with this approach is that although we still have a natural cost function here, instead of minimizing the energy, now we minimize the Gibbs free energy. This is a much more difficult quantity to measure because it contains the entropy, and the entropy is notoriously challenging to measure on a quantum device. So that's been one challenge with trying to realize Gibbs states in variational approaches. But what we noticed in a recent work here, just came out a couple of weeks ago, is that we can replace the free energy with a new cost function, which is shown here, where this does not depend on the entropy. And in particular, there's no log of the density matrix appearing here. And it only depends on the purity of the state, which is straightforward to measure, as well as this trace of the Gibbs ensemble with rho. And although it might naively seem like we need the answer to our problem, this Gibbs state, in order to compute the cost function, this is actually not the case. We can do a simple Taylor series expansion of this expression, and we find that we can stop at third or fourth order and still get very accurate results. So this circumvents all the challenges with trying to measure entropies. And here are some results of ADAPT applied to this Gibbs type problem. So here we looked at two different types of spin Hamiltonians, an Ising spin chain here on the left has periodic boundary conditions, and an XY type system, also periodic, and 4 spins in both cases. Now, in order to prepare Gibbs states, we need to, in addition to our 4 data qubits, we need ancillary qubits in order to create mixed states. And in the extreme case, we needed an additional 4 such ancillary qubits to create a completely mixed state. But it's interesting to ask, can you get away with using fewer ancilla qubits, and can you still accurately represent the Gibbs state you're after? So here, in the case of the Ising spin chain, this is a plot of the fidelity of the resulting state compared to what we're trying to get as a function of the temperature, inverse beta. And we see that in the case of using 4 ancilla qubits, we always get very close to unit fidelity. But then as we reduce the number of ancilla qubits, the fidelity goes down at higher temperatures, which is expected. But interestingly, what we see is that, so the solid lines here correspond to the theoretical maximum you can achieve given this limited ancilla register. And so ADAPT is systematically able to maximize the fidelity given that constraint. And then if we look at the number of C0s, we see that the C0 count can be very low, especially if we use this reduced ancilla register. And it can be very low, even in the regime of low temperature, which is usually considered the more challenging side, because here we have states which are very minimally populated with an exponential decay from the Gibbs ensemble. And so we're still able to get really accurate results down in this regime, even if we have a reduced ancilla register. And in the case of this periodic XY Hamiltonian, we see very similar results. So this approach to Gibbs state preparation seems very promising. Okay, I also wanted to briefly mention optimization problems. So going away from chemistry type problems or spin models, can we solve classical optimization problems using these adaptive algorithms? So a classic example of this is the max cut problem, where given a graph, we're trying to figure out how we can divide the vertices into 2 sets such that we maximize the number of cuts across edges. And this kind of problem can be represented as an Ising spin chain or an Ising spin type model with a cost function shown here, where basically this is just accounting for how many edges are cut for each possible cut, and each possible cut corresponds to a product state. And so the ground state of this Hamiltonian represents the solution to this max cut problem. And we can generalize this to edges that have different weights and try to minimize the energy of this cost function instead. So there's a well-known algorithm for trying to deal with these types of problems called the quantum approximate optimization algorithm, or QAOA. It's inspired by the adiabatic theorem. The idea is you start from an initial state of all pluses for all the qubits. And this, of course, is an eigenstate of this operator, the sum of all x poly x's. And then the ansatz for QAOA has this alternating operator structure. So you start off by applying the cost Hamiltonian exponentiated, and then you follow that by this so-called mixer term, which is the sum of all x's in the exponent. And then you just go back and forth between these two operators. And each operator comes with an optimization parameter that has to be tuned. And so then we perform a variational quantum eigensolver algorithm to tune these parameters to minimize this cost function, and thus find the solution to the optimization problem. Now, to make this an adaptive approach, what we did is we define, instead of using this standard mixer of the sum of all Pauli x's, we define a mixer pool, which can be comprised of single or 2-qubit gates. So we consider both kinds of pools, only single qubit gates or both single qubit and entangling operators, 2-qubit operators. And then using these pools, we found that while using single qubit gates only in the pool does not give a significant improvement compared to standard QAOA, we found that if we use these entangling operations in the pool, we get much faster convergence, as shown in the green curve here. And this is true for several different problem instances. So here we're averaging over the edge weights of a 6-vertex graph that's fully connected. I'm sorry, not quite fully connected, of degree 3 in this case, fully connected in the case on the right. And in both cases, we get convergence after 3 or 4 layers, whereas standard QAOA never quite converges out to the times that we considered. And then if you do an analysis of parameter counts and C0 counts, we find that ADAPT always significantly outperforms the other approaches, basically because it's converging so quickly. Okay, and then in the last couple of minutes, I wanted to briefly mention our work on going beyond digitized gates and using this algorithm called ctrl-VQE. So hardware is currently very noisy, even for variational quantum algorithms, which are designed for near-term devices, at least in principle. And the basic idea behind ctrl-VQE is to just throw away the state preparation circuit. Stop talking about gates, and instead think about pulse level optimization. So try to prepare the state on the quantum processor by taking measurements of the Hamiltonian, but then use those measurements to directly inform how the pulses themselves should be updated, pulses being applied to all the different qubits. And keep repeating this process until we reach convergence. So this is very much what is typically done in the field of optimal control theory. So here we just want to apply it to quantum simulation type problems. And so here are the basic ingredients for ctrl-VQE. We start by, so here we have to update the pulses. We have to know what is the hardware Hamiltonian that we're considering. And we usually focus on superconducting transmon qubits for concreteness. And then we pick how we drive the system. In this case, we considered microwave drives to each of the transmons. And then our cost function is the molecular energy. So we just keep updating these pulses in some systematic way that I'll clarify in the next slide until we reach the lowest energy and get an approximation to our ground state energy. So in practice, how we do this is we fix the pulse amplitude, we fix the pulse duration. And now to provide pulse flexibility in a systematic way without having too many parameters up front, what we do is we randomly divide the pulse into 2 parts. So the time at which we split the pulse is chosen random. And then we allow the amplitudes to be optimized independently for these 2 parts. So we get something like this. And then we repeat as needed. We again randomly pick a point to split the pulse. We split it, we let the amplitudes be optimized independently, and we keep going. So this provides an adaptive algorithm that's purely control-based. And we can keep repeating this until we find convergence. And we did this for a few different small molecules, including H2, lithium hydride, and so on. And we find that we can systematically reach chemical accuracy very quickly using very few time segments. And if we compare in real time what this looks like compared to using a gate-based approach like UCCSD, what would require 80,000 nanoseconds of evolution in the gate-based approach translates to only 50 nanoseconds using ctrl-VQE. So this is a more than 3 orders of magnitude improvement over gate-based approaches. So this is the real motivation for trying to eliminate the gates and just go directly to the control hardware. And then I'll briefly mention that we also studied what happens as we go to the quantum speed limit. I won't spend too much time on this, but basically what happens is as you keep reducing the pulse duration time, smaller and smaller, we find that the optimal pulses form a bang-bang type behavior. So they switch back and forth between the two amplitude bounds that we impose. And we find that this formation of a bang-bang type structure is fully consistent with the Pontryagin maximum principle. And we did an analytical calculation to confirm that it's behaving exactly as expected. Now, one interesting thing we noticed is that allowing for leakage out of the computational subspace can actually speed up the reaching convergence. So on the left, I'm showing results for qubits. So here I'm still talking about a transmon system, but I truncate each transmon down to just a 2-level system and optimize the pulses in that situation. And we find this bang-bang structure, but we find that the minimal pulse duration in which we can still find solutions is 15 nanoseconds in this case. But now if we include the 3rd level of each transmon and rerun the algorithm, now we find that we can get solutions all the way down to below 9 nanoseconds. And then as we approach 8.94 nanoseconds, again, this bang-bang structure emerges. So what this is showing is that by including the 3rd level of the transmon, we can actually get to the target state faster. So leakage seems to be speeding up ctrl-VQE. And we did this also including higher and higher levels in the transmon, going up to 5 levels. We don't see any real change between 3, 4, and 5 levels, but there's a big change between using only 2 levels. So having some leakage out of the computational space is really important for getting the speed up. And we can understand the speed up in a very simple way. There are actually a couple of contributions to it, but I'm going to focus on just the main one and the simplest one, which is that essentially what we're doing is we're saying in these simulation problems, because it's variational, I don't really care if I have leakage, because so long as if the footprint in the computational space is what it's supposed to be, it's the ground state of the problem I'm trying to solve, then that's good enough. And so by allowing for leakage, I'm actually just expanding the space of acceptable solutions in Hilbert space. And some of those states in that expanded space can be reached more quickly compared to the ones that are purely within the computational space. So that's a rough way to understand why the speed up occurs. But it's an interesting and unusual scenario in which leakage is actually beneficial. Okay, with that, I'll conclude. So I talked about 3 different ways to improve the performance of variational quantum algorithms for simulation. Symmetry enforcing circuits. So we build the symmetries directly into the circuit and expand the symmetry subspace exactly once using the minimal number of optimal parameters. I talked about these adaptive algorithms called ADAPT-VQE and Qubit ADAPT, where we build up the ansatz 1 operator at a time using measurements of the quantum device. So in a way that's tailored to the problem being simulated. And then finally, I mentioned ctrl-VQE, this idea that we get rid of the gates in the state preparation circuit entirely and just directly optimize the pulses to create the state that we want to create on the quantum processor. All right, with that, I'm happy to take any questions. Oh, and let me acknowledge the group that did all the work. In particular, Vlad Shkolnikov did all the work showing minimal complete pools, all the proofs and all of that, very impressive work. Holun, Sam did a lot of work with Qubit ADAPT and also with ADAPT QAOA. And Chenshu and Ayush did all the work related to ctrl-VQE. And Harper was on the original ADAPT paper, and he's been doing all kinds of amazing stuff with it too. All right, I'm happy to take questions.
All right, thank you, Ed. Let's thank the speaker before we get into questions here. So I guess so. It looks like Ryan has a question. Ryan, do you want to go ahead?
Sure. Thanks, Ed. This is really interesting. Could you go back to the slide where you were? It was about the completeness of the pool. You showed that if you take all the nested commutators and it generates the Lie algebra. Yeah. Oh, yep. I think that was it. Yes. So. So you can form the exact ground state when the states form a complete basis. So, so complete basis meaning you have enough basis states to form. Does that mean you have like 2 to the n basis states?
So yeah, so in the general case where I'm trying to span the entire Hilbert space, it means 2 to the n. But if I'm imposing symmetries, then it can be much smaller than that.
Okay. So does that mean you need to have 2 to the n factors on the left side of that equation to have 2 to the n independent parameters?
So that's,
I guess where I'm going with this is that even if your commutators generate all the different basis states, if you don't have enough independent parameters, you may not be able to reach every part of the Hilbert space.
Yeah, so there's an important caveat here, right? So here I'm not interested in writing and constructing an ansatz that can represent every state in Hilbert space, right? What I want to do is go from some initial state to some target state. And that generally requires far fewer than 2 to the n parameters. I don't know, is the distinction clear?
Well, I guess, but if it's an arbitrary state.
Right. So in ADAPT, I'm not interested in trying to create an ansatz that can represent every state in Hilbert space. I want to go from one state to another state as quickly as possible. But in order to guarantee that there is a link between those two states, I want to have this flexibility to be able to create, you know, any generator in the Lie algebra.
Okay, I mean, I guess.
So this is what's different compared to like the symmetry enforcing circuits I talked about. So the symmetry enforcing circuits there, I'm talking about making a fixed state preparation circuit with some exponential number of parameters that exactly spans the symmetry subspace once. But in ADAPT, we're skipping that part because in ADAPT, we no longer try to represent the entire Hilbert space or symmetry preserving Hilbert space. Instead, we're trying to make sure we can create a path from one state to another state. But I need to make sure that my ansatz has enough flexibility to create all kinds of different paths. So the actual number of parameters that enter into my ansatz is much, much less than 2 to the n.
Well, in some sense, but I mean, if that state is completely arbitrary, then there's, in some sense, still the full Hilbert space worth of degrees of freedom that needs to be available. That's what I'm not quite making the connection on. I can.
Right, but if I needed 2 to the n operators to go from the initial state to the final state, that means I'm essentially wandering through all Hilbert space until I end up at the state I'm trying to get. But that's not the way ADAPT works, because ADAPT, it uses this gradient criterion to figure out what's the best direction to move in. It doesn't kind of randomly sample from Hilbert space.
Okay, all right. I think I sort of see it, but I'll have to think a little bit more. But thanks for answering.
Yeah. But one thing I would add though is that we don't have an answer to how many iterations does ADAPT need for a given problem size. That's an open question.
So Ed, I actually have a question here. So I kind of following up from Ryan's question. Have you thought about sort of I guess reachability or even aspects of controllability and sort of what one can say about ADAPT from those sort of I'd say standard control I guess control techniques or control quantities that people look at?
So you mean like thinking about these landscape type questions that I was touching on a little bit?
Yeah, so I guess I'm wondering here, you know, for example, as Ryan said, you have some state that you're trying to produce, that's some arbitrary quantum state that you want to reach, and you know, you form this basis, but you say, you know, for example, you don't want to have 2 to the n possible parameters, and so what you're asking is basically, let's say I truncate this the number of variational parameters I have. To say I have k parameters, and sort of what is the reachable set of possible you know of possible states that one can obtain from that. I mean, I know that, you know, in your case you're sort of moving in a particular direction, but you're also limited in sort of what accessibility you have to the space, because you are limiting the space of operators that you have too. So I'm just curious to know, like, have you sort of thought about this? And I guess one way of looking at it, I guess, is just looking at these landscapes, which I think this is the way that maybe it's Herschel Roberts has looked at this like this. I can't remember whose group it was. Yeah. Okay.
Yeah. So I think the point of the complete pool story is that there we want to make sure we have enough flexibility in the ansatz and in the pool so that we can go from any state to any other state. That says nothing about how many parameters we actually need at the end. But I think that's a bit different from this trainability issue, because I think trainability is more about what does the landscape look like. And what we found is that because the adapt ansatz is very short, there's a general expectation in optimal control theory, which is that if you have a lot of parameters, exponentially many, then the landscape becomes nice and smooth. That's one of the big results that the rabbits talks about. And so there you expect the optimization to be easy. But in the case of ADAPT, we're actually trying to do the opposite, right? We're trying to make the number of parameters as small as possible. And so as we're showing in this plot here, the landscape is actually very rugged. And then, initially that can seem worrisome for the performance. But what we find is that because ADAPT, is building up its ansatz on its own, essentially, and deciding what's the best direction at each step, it's actually deciding what's the best landscape. It's creating the landscape on the fly, and it does so in such a way that the current state is always close to the global minimum of that landscape, and you never really explore any of these bad regions. But if you were to just take some ansatz that ADAPT produces and just free up all the parameters in that ansatz, forget about what the optimal values were in the previous iterations and so on, and just explore that landscape, that's essentially what's happening in this plot here. You can see that the landscape is a mess, and it would be, if we were starting in some random point in that landscape, it'd be hard to optimize. But ADAPT does not start at random points in parameter space. But I don't know if that's really answering your question, Greg.
I think a bit, I guess, but it's fine. I think we can always take this offline. I guess Dimitri, it looks like you have a question as well.
I think, yeah, just follow up. So I would assume there is a direct relation how much entanglement you can build, right, with the length of the sequence of this elementary adaptively dynamically added unitary operators, right?
Mm-hmm.
So which kind of goes back to reachability, like what kind of states you can reach given the finite lengths of the sequence of the unitary operations.
Mm-hmm. Yeah, so if you're using a complete pool, that means you can create any amount of entanglement in principle, because you can go from any state to any other in Hilbert space. That said, it's interesting to ask, is there some way to restrict the pool size to below the minimal complete pool size of 2n minus 2, such that you still can generate enough entanglement? Strictly speaking, if you think about chemistry problems, the amount of entanglement in the ground state of a molecule is actually pretty small compared to sampling just generic states in Hilbert space. And so if there was a way to choose the pool so that you're only focused on these lower entangled states, that'd be kind of interesting. Another place where this enters in is when I talked about optimization problems. So there, in this ADAPT QAOA type approach, or even in regular QAOA, what we're doing is we're starting from a product state and we're ending up in a product state, because we start in the state of all pluses on the qubits for QAOA, and then we know that the answer to the optimization problem is just some bit string, which tells us how to cut the edges in max cut, for example. So we're going from product state to product state, but then we're doing that using these entangling operators. C is the cost Hamiltonian. It has Pauli strings of weight higher than 1, and so it creates entanglement. So these quantum approaches to optimization, they seem to create entanglement and then get rid of it. And the claim seems to be that this gives speed up, and that's certainly been the case for our own simulations. We find we converge pretty quickly, but I think it's an open question, how much entanglement do you need to get this kind of speed up, and what exactly is it doing? So yeah, I think that's a really interesting question.
Okay, thanks.
Is there one last question for our speaker? Okay, all right. Well, thank you again, Ed, for the wonderful talk. And of course, if you have any questions, please follow up with Ed or myself, and I can forward you Ed's information. Okay, thank you everyone, and see you again next month. Bye-bye.
Thanks a lot.